So in the last lecture, we started with the Hebbian learning rule, right? So what is the Hebbian learning rule? What is the weight update equation for the Hebbian learning rule? Yes. What is delta W? Yes, students.
The learning rate multiplied by the activation function multiplied by the input.
Okay. So learning rate CRX. Don't forget that equation of the general learning rule. The weight update equation for the general learning rule is CRX. C times R times X. Where what is C? C is the learning constant, R is the learning signal, and X is the input vector. Okay. And for Hebbian learning rule, the learning signal is going to vary for each learning rule. Depending on the learning rule that you're going to use, R is going to vary. So R for Hebbian learning rule is nothing but the activation function. It's the output. R is nothing but the output of the network, O. And what is O? R is nothing but it is O, right? R is equal to O. And O is nothing but F of W transpose X, right? So this is the Hebbian learning rule. We also solved a problem on Hebbian learning. And by the way, it is based on some experiment, psychological experiment. What is that experiment called?
Classical conditioning experiment.
The experiment of classical conditioning done by Pavlov. Okay, so don't forget this. The basis for Hebbian learning rule is psychological experiment conducted by Pavlov on his dogs. Okay. Don't forget the video that we saw. Now today what we will do is we will move ahead and we will look at the next learning rule, that is the perceptron learning rule. Okay, and we'll be solving problems based on perceptron learning. So perceptron learning rule we have seen earlier. Let us quickly revise it. Okay, so it is the perceptron model is based on the perceptron learning rule, where the learning signal R, it is the difference between the desired output and the neuron's actual output. Okay, now what happens in this case is you have a label associated with the data. In the case of Hebbian learning rule, what is the type of learning rule? It is unsupervised, because we didn't talk about any desired output, right? We didn't talk about the target for each input pattern. But in the case of perceptron learning rule, you have a desired output. So the learning signal is the difference between the desired output and the neuron's actual output. Okay, so it is supervised. And remember, how is the output computed in this case? In the case of Hebbian learning, we can use any activation functions which are any of the activation functions which are there. But in the case of perceptron learning rule, it's binary in nature. The perceptron, the initial perceptron which was proposed by Rosenblatt, it is binary in nature. So the output of this neuron, the neuron in fact is binary. The output of this neuron is binary. Okay. So which function you can use for this? The step function, the sine function, right? So perceptron learning rule uses the step function or the sine function. either bipolar or unipolar, depending on how you are tagging the targets or the desired outputs, right? So the output of this particular neuron, the perceptron, is sine of W transpose X, sine of that. It's specifically the step function. Okay, and learning signal is of course D minus O. So the weight update equation accordingly will be, in this case, C times again the learning signal times X, C times the learning signal R times X the input. So for all the, so this is giving the individual weight changes for all the inputs. Okay, so for all the inputs, input features which are there, you will have to compute this, apply this. So it's talking at the individual level. So if you want to draw it and depict the perceptron, it looks like this. So you have your single neuron, which is having these input features with the weights, and the output, whatever the net value that you're computing. What is net? Net is nothing but this weighted sum of inputs is called net activation. Okay, and that is passed through an activation function. The weighted sum of inputs is computed for every model that you have, every neuron model. Any model that you have, first step is to compute the net value. That is nothing but the weighted sum of inputs, right? So once you compute this net, you pass through the activation function. But for the perceptron in particular, you make use of the step activation function. Okay, so once you pass it through this, you get the output, and this output is then used along with the learning, the desired label that we have to get the learning signal, that is R. Okay, so D minus O. D is the desired output. O is the output that you have got through the network. So D minus O times C times X, the current input vector that you have passed, is nothing but delta W. So diagrammatically, you can depict it as this particular diagram. Okay. Now, if you want to simplify this equation, see, since we know that the functions that are available to us are either unipolar binary or bipolar binary, what we can do is we can simplify that equation, C times D minus O, right? We can simplify it because we know that the output for a step function will be either a +1 or a -1, or it will be 1 or 0, depending on whether it is bipolar or unipolar. Okay, so let us simplify that equation and see what we get. So if the unipolar binary activation function is used, that means either there's a 1, the output is a 1, or it is a 0, right? So in that case, delta W, when you substitute that value, okay, you substitute the value as 1 or 0 in this equation. Okay, when will it be 1 and when will it be 0? When will the output of this function be 1? When the net value is greater than or equal to 0. The output will be 0 when it is less than 0. The output of the function will be 0 when it is less than 0. Net value. What is net less than 0? Net value. Yes or no? One more thing that you should remember, that whenever you're updating the weights, you update the weights only if your outputs do not match. Because if they match, then D minus O becomes 0, right? So if you're getting the correct answer as the output, you will not update the weights, right? Yes or no? So D, only if D is not equal to O, you are going to update the weights. So if you are updating the weights, if D is equal to 1, okay, if D is equal to 1, you know that D, you are updating the weights when D is not equal to O. So if D is equal to 1, that means O is equal to 0. The output that you have got is 0. And the desired output that you have with the label that you have is 1. Okay. So when you substitute these values, what will you get? The value of delta W will be C times X. Yes or no? When D is equal to 1, the output will be, the weight update will be C times X. And in the other case, that is when D is equal to 0 and O is equal to 1, you will get it as minus Cx. Yes or no? Okay. So delta W is equal to plus or minus Cx. And the sign of this term depends on what? The desired output. Yes or no? When D is equal to 1, it is plus Cx. When D is equal to 0, it is minus Cx. Correct? So this is the case when the unipolar binary activation function is used. Now, if we use the bipolar binary activation, can you quickly tell me what will be the value of delta W? Using this similar logic, what will be the value of delta W? Yes. The bipolar binary activation function output is plus 1 or minus 1. Bipolar binary output is plus 1 or minus 1, right? So what will be the answer for delta W? Simplified equation. Yes? Someone? Just substitute the values here.
Okay.
Yes?
लाइक ओ क्या होगा मुझे समझा नहीं, लाइक अगर वो D +1 है तो O क्या -1 होगा?
Yes.
So it will be
What is
0.
O? No. What is the output O? O is nothing but the output of the network. And what is the output of the network? The activation function applied over the net.
Okay.
Yeah. So
2
plus
times.
and plus or minus 1 it will be. You are applying the activation function over the net. So D will be the label. Label will be either plus 1 or minus 1. So it will be O. See, when are you going to update the weights? You're going to update the weights when D is not equal to O. So matlab, what happens is you're giving one pattern. Let's say you give a pattern to the network. Network has produced output plus 1. Okay. But the output, the desired label with that desired label with that particular pattern is a minus 1. The desired label with that is a minus 1. So in that case, what will happen? There's a mismatch between the actual output, what the network predicted, and what the label is. There's a wrong prediction, right? So in that case, you need to update the weights. So when you're updating the weights, yeah.
No, ma'am. Sorry, you were explaining. I was gonna say the answer, but never mind now.
Okay. So when D is not equal to O, we have got these equations for unipolar binary, because the possible answers are outputs are 1 or 0 na, for unipolar binary. And in case of bipolar binary, it is plus 1 or minus 1. Desired labels also will be in that fashion only, plus 1, minus 1 or 1, 0. Understand that what we are talking about, the perceptron learning rule, and we are talking about only a single perceptron, only a single neuron. So what are the two possibilities? Either it belongs to one class or no, it does not belong to that class. A single perceptron is capable of classifying in only two classes, yes or no? Is this logical? A single perceptron is able to classify into only 2 classes. Yes or no?
Yes, ma'am.
So we are talking with respect to only a single perceptron. We have not talked about the neural network now. All these learning rules we will talk with respect to single neurons. Okay. So now delta W, you have got how it has come out to be plus or minus Cx in case of unipolar binary. Because there will be 2 classes only, and you label the classes as 0 or 1, since it has to match. Now you see, how will you understand whether the prediction which is made by the network is the same as what label you have given it? In that case, the labels have to match the prediction. No? So the labels have 2 possible values, 1 or 0, because the possible predictions are also 1 or 0. Are you getting this? In case of unipolar binary, are you getting this concept?
Yes, ma'am.
So on similar lines, if I use a bipolar binary activation function, then what will be the possible labels?
It will be 2cx and minus 2cx.
That is the answer. You are giving the answer. What will be the possible labels? The desired output.
Labels.
Plus or minus 1.
Yes, ma'am.
Right? 2 classes, plus or minus 1. Also, the output possible also will be plus or minus 1, because we are using the bipolar binary activation function. Okay. So just substitute in this equation and you will get plus or minus 2cx. Plus minus 2cx. That is what you get. Is this clear to everyone?
Yes, ma'am.
Yes, Harsh, it is clear?
Yes, ma'am. Yes.
Okay. So let us move ahead and use this to solve problems. So the first problem that we have here is 3 input patterns are given, x1, x2 and x3, and the initial weights are given. So the initial weight vector is also given to you. Apart from this, the labels will be given. Since it's the perceptron learning, for each pattern that we have, there will be an associated label. So these labels are given here, D1, D2 and D3, right? So D1 is minus 1, D2 is minus 1 and D3 is 1, right? 2 classes, either minus 1 or plus 1. And the learning constant is given to be 0.1. Okay. And you have to compute the weights after one cycle, one complete cycle or one iteration. So to proceed, we can either solve it using the way we solved Hebbian learning, stepwise. That is, stepwise you're going to multiply the weight vectors with the initial with the input patterns and then apply the activation function, or you can do it in the form of a table. Okay, so we can just conveniently write everything in the form of a table. So what we do is we just write the steps 1, 2, 3, because there are 3 patterns, so there will be 3 steps, right? So in that epoch, in each epoch, there will be 3 steps. So 3 patterns we'll write. This is x1, this is x2 and x3. And then we'll do all the computations which are required. Row wise, we will write all the intermediate outputs. Okay. So so in order to proceed, we'll follow the same steps. Only thing is we are tabulating it now. So it is up to you whether you want to solve it in this fashion or the other way. Okay. So just we'll solve it today in using this table, so that you are well versed with both ways of solving. So X and W. So first step is you compute net, right? So what is the net value? I'll present again. Okay, you multiply this. This is the first vector, multiply the individual values, sum it up and tell me the net value. What is the net value? We'll solve it. The initial weight vector is given to us. I've just put it in the table. You tell me what is the net value.
2.5.
2.5. Right. So it is 2.5. So based on this net value, you will compute the output O. What is O? O will depend on which activation function you are going to use. Now, in this particular example, the activation function was not mentioned, right? But what is given to you is the desired outputs. The desired output labels are mentioned. They are +1 and -1. So which is the activation function?
Bipolar, binary bipolar.
It is bipolar binary. So what is the answer for this? The output is equal to f of net. Net is greater than or equal to 0. So it has to be a +1. Output is +1, right? So now, is there a match or mismatch between D and O? It's a mismatch, right? They are not matching. D is -1. This is 1. So you update the weights. What is the equation for weight update? Shorthand equation. It is plus or minus 2cx. But in this case, it will be minus 2cx. Yes or no? Because the sign depends on D. The sign of that equation depends on D, the desired label. Okay. So minus 2cx. In this case, it is minus 2cx. So use that. C is given to be 0.1. Right? C is 0.1. So use that 0.1 into 2, minus 2cx. Minus 0.2 times x. X is here. This is x. Okay. Tell me the values of this vector one by one. Minus 0.2. Right? Minus 0.2 multiplied by x. That is what we are doing. Minus 0.2. Next is 0.4. Next 0. And finally fine. So this is the delta W that we have computed. This is delta W. And in order to get W, we need to, the next W, we need to add this to the weight, or original weight vector, right? That is this. So this plus this will give me the new weight vector that we are going to write here. Okay. So tell me what is the new weight vector? So it will be 1 plus minus 0.2. So that is 0.8. Okay. Just look at it. Then W, look at the column. So minus 1 plus 0.4. That is minus 0.6. Then 0 plus 0. That is 0. 0.5 plus 0.2. That is 0.7. Correct? Now, we have the next pattern. So, for the next pattern, add this next pattern. Multiply these two these two vectors, the pattern vector and the weight vector, and get the value of net. That is the first step. So, do that. What do you get the value of net? What is the value of net that you get?
minus 0.79.
Minus point? No.
799.
This is 0. This is 15 6 are 90 point minus 0.9, and then this is 0, and this is minus 0.7. So it is minus 1.6, right?
Yes, ma'am. Minus 1.6.
Okay. Based on this, what is the output now? Output is
Minus 1.
okay. So is there a match or mismatch?
Match.
Match. So we will not update. It will be 0 basically, right? So the weights in the next step will be the same weights. Weights will not change, right? So just copy this here. And then compute the net as usual for the third input pattern. Okay. So third input pattern, again just multiply the corresponding weights and the inputs. What are you getting as a net value? Multiply this with this, sum it up.
Minus 2.1.
Minus 2.1. Okay. Output is minus 1.
Minus 1.
Now there is a mismatch. So what is the equation? Is it plus 2cx or minus 2cx?
Plus 2cx.
Plus 2cx. Depends on D. Okay. So plus 2cx, C is 0.1. So 0.2 times x. 0.2 times x, that is this pattern. Just multiply each of these elements with 0.2 and you will get delta W3. This is delta W1, delta W2, delta W3 in terms of vectors, weight vectors. These are small w's, okay, whatever I have written here. These are the individual weight elements of the vector. Capital W is used to represent the vector. Similarly, these are small x values. Small variable is small case, right? Capital X represents the vector x. So tell me 0.2 times this. So it will be minus 0.2, 0.2, right? 0.2 times 0.5. What is it?
0.1.
0.1 and minus 0.2. Next, the last step is to find the weights. Remember, the goal of all this problem solving ultimate aim is to find the final weights of the network. Final weights will be W4, that is this weight plus this weight. Okay. What is it?
0.6.
0.6
Minus 0.4.
minus 0.4.
0.1. 0.5.
Right. So this is how you solve. So this is another way of solving the problem. You either do that first way where we are solving stepwise 1, 2, 3, or you can solve it in the form of a table. Only thing is when you're solving in the form of the table, just write the equations carefully. You can write it here. I have not written the equations here for your reference so that you don't make a mistake. This looks more concise, but it depends on how you are comfortable with it, which method. You can choose anyone. Okay. So the next problem I have chosen is a little different. So I have included this problem here. We'll solve this problem. So look at the question. So the input patterns and the desired outputs are given to you. Okay. And the final weights are given to you. So after training for one iteration, W4 will be the weight vector that you get after one iteration of training. So that is given to you. Apart from this, it is also mentioned that knowing that correction has been performed at each step, determine the following weights. C is given to you, learning constant. You determine the following weights, W3, W2, W1 by backtracking the training. Okay. It is given that correction has been performed at each step. So what is the meaning of this statement? The meaning of this statement is at every step that a pattern was presented, there was a wrong output prediction. Right? Correction means correction in the weights. Okay. So correction was performed at each step. That means there was a mismatch at every step of training. For each of the input patterns, there was a mismatch. So D was not, whatever the network was predicting was not equal to the desired output D. O was not equal to D in each step. Okay. Given this particular information, this additional information, you are required to compute W3, W2 and W1 by backtracking the training. So initial weights are not given to you. Final weights are given to you. You need to backtrack the training and you need to compute the weights, which were the weights in W3 in step 3, 2 and 1. And the second part is the standard way that we do it. That once you do this, you just compute W5, W6, W7 by just moving ahead, by reusing the same sequence. Second part is easy. It's the usual way that we solve the problem. But the first part is slightly different. You just have to backtrack the training. Okay. So now, two tables I have with me. First is the backtracking part that we need to solve. Okay. So W4 is given to you. W4 is this vector 3261. They have given this to us. Okay. And we know that the sequence was x1, x2, x3. Okay. So x1, x2, x3 was there with us, but we need to backtrack. So what we will do is we will try to we'll have to compute these values, right? We need to compute delta W's in each step. So how do we do that? We will just reuse our equations. We'll rearrange the terms in our equations to get the delta W values. So we know that W4 is equal to W3 plus delta W3, right? This is how we write the equation of weight update. W4 is W3 plus delta W3. So what is delta? We have W4 with us, right? What about W3? What is W3? W3 will be, we rearrange this equation. So W4 minus delta W3, right? We can compute W3 by reusing this equation. So W4 is there with us. What about delta W3? Do we have that term with us? We do not have delta W3 with us, right? But we know one thing. One information is shared with us, that correction was performed at every step. So if you know that correction was performed at every step, can you compute delta W at every step? What is the equation for delta W? Plus or minus 2cx? Equation for delta W is plus or minus 2cx? Yes or no? Delta W is plus or minus 2cx, and it is given to you that every time the weights were updated. Okay. X is there with us. We have the desired label with us. So out of these plus or minus 2cx, which equation should we use? It depends on the value of D. Yes or no? Whether to use plus 2cx or minus 2cx, we can understand that easily because we have D with us. Okay. So in the first case, what is the equation that you're going to use? Minus 2cx, because the sign of d is minus. It's minus 1, right? So when d is minus 1, it is minus 2cx. Okay. So minus 2cx, if you use that equation, can you tell me what is the value of delta W3? Equation for delta W. I'll just write it here for your reference. Okay. So in this case, it is minus 2cx. In this case, it is 2cx. And this is also minus 2cx. Okay. Now you tell me what is this vector. C is given to be 1. C is given to be plus 1. 1. Okay. Take this x. Inputs were presented as x1, x2, x3, but this is input 3. This is input 3 because we are backtracking the training. So when we obtained W4, we obtained it via pattern x3. Okay. So x3 we are using, we are computing delta W. What is it? Substitute the values. Minus 2cx. So it is 4062. Okay. Now that we have this vector with us, we can easily compute W3 using this equation that we rewrote. Okay, so W3 is nothing but W4 minus delta W3. So W4 is there with us, delta W3 is there with us. We can just subtract these two and get W3. This is W3. Okay. So W3 is, subtract those two values and tell me what is W3. 3 minus 4, right? Minus 1. Next, 2 minus 0, that is 2. 6 minus 6, that is 0. Are you getting it? 1 minus 2, that is minus 1. Okay. Next. You have W3 with you. Okay. Now you have the second input pattern. What do you need to compute? What will you compute? Delta W2. Can you compute delta W2? First thing is you will compute delta W2 because you will get W2 by rearranging that equation for W3. Yes or no? That means below this you will have more equations. Right? So W2 is W3 minus delta W2. This particular equation you're going to use in order to get W2. Simply first find delta W2. So delta W2 is nothing but 2cx. So use this equation with our second pattern and obtain delta W2. Okay. So it is 0, minus 2, 4 and minus 2. Correct? Using this, write the vector W2. This particular vector minus this vector will give me this vector, right? So write what is the value? Minus 1 minus 0, that is this. minus 1, 2 minus minus 2, that is 4, 0 minus 4, that is minus 4, and minus 1 plus 2, that is 1. 1, 4 minus 4, 1, right? This is correct. Similarly, what you need to do is use the same logic and compute W1. So W1, first step will be to compute delta W1. Delta W1 again is minus 2Cx. So minus 2Cx, you apply to this pattern, x1, this is x1. Okay. What is the value that you are getting? Minus 2, 4, minus 6, and 2. Right? And now just subtract these two vectors, you will get W1. So minus 1 plus minus 1 minus of minus 2, that is 1. What is the vector W1? Can anyone tell me? 1,
102 minus 1.
102 minus 1. Okay. So that is W1. So this is how you will solve this problem by backtracking. Second part, tell me what is the value of W5. Second part is straightforward. You just have to do it in the usual way. You have W4 with us, you just proceed forward. Just proceed forward. So W4 you will take as the initial weights, present x1, get the next the predicted output, the delta W values, and then find the new weights, and so on. What are the new weights after giving the first pattern now? 3261. What is the net value?
मैम बट लाइक x इसके आगे के इनपुट्स नहीं दिए ना, तो सेम इनपुट यूज करना है.
उसमें लिखा है you have to use the same inputs by reusing the sequence x1 b1, right? Same inputs are given. What is net? Multiply this with this. Tell me the net value. Three minus 4 is minus 1 plus 18, which is 17, minus 1, that is correct. Are you getting 16?
Yes.
Okay. So 16 is the net value. What is the output? Output is plus 1. Okay. So apply, desired is given, desired output is minus 1. So it is minus 2Cx. Use minus 2Cx and compute this. So minus 2 times this. What are you getting? minus 2, 4, minus 6, and 2, right? Add these two weights, W4, and this is delta W4. Add these two weights, you will get W5. This is W5. Rather, I'll write this here so that it's not confusing. Right? Add these two, you'll get the new weights. Tell me. So 3 minus 2, that is 1, right? 2 plus 4, that is 6. 6 minus 6, that is 0. 1 plus 2, that is 3. Okay. Now you compute new weights. New weights are there. The net value. You will compute what is the net value. What are you getting as net? Just multiply these two. This is 0, minus 6, minus 3. It is minus 9, right? So output is minus 1. Output is minus 1. So there's a mismatch. What are the weights? Delta W. What is delta W? 2cx. So 2 times x, because c is 1. So 2 times x, this vector. So it is 0, minus 2, 4, and minus 2. Right? Next, delta W plus delta W, you will get the new weights. What is that? Just add the vector. So it is 1, 6 minus 2, that is 4, 0, 4, that is 4, 3 minus 2, that is 1. Net value is multiply these two and add them up. So minus 2 minus 12 is minus 14, minus 1 is minus 15. Is it minus 15?
Yes.
Minus 14 or minus 15?
Minus 15.
Okay. So this is minus 1. They are matching. So weights will not change. Right? So what are the final weights? They are 1, 4, 4, 1. W7. This is W4, W5, W6, W7. So they remain change. Remain the same. Okay, unchanged. So this is how you proceed. So today what we have done is we have seen how to apply this for problem solving. In the next lecture, we will just delve more deeper into this perceptron learning, and we will look at different elements which are required as part of training the network using perceptron learning. Okay. Because we have not discussed the details which are involved. We will discuss it a bit more in detail and understand the concepts like bias which are required for perceptron. So that's all for today. We meet in the next lecture.